Dealing with quite a bit during this chapter is parametric curves. And using them to get to Green's theorem. And we've actually stated Green's theorem in different ways, three different ways. This is one of them, and this is another. Actually, all right, so both of these are Green's theorem, and then there's the third statement, the original statement besides that. And where we're trying to get to by the end of Stewart is this. In both these cases, we have a flat region in the plane, D, and some boundary curve C, and we're relating an integral over a curve to an integral over the region inside it. So what we're trying to get to by the end of a chapter is this, that we have an integral over a space curve, because here this is 2 dimensions, this is a plane curve. But here we're dealing with a space curve, a curve that sits in 3-dimensional space rather than 2. And we're going to relate that to an integral over a surface of a curl of a vector field dotted with the normal vector. So we have some surface sitting in space. I described it as a Pringles potato chip last time to give a concrete example. And you have a vector n that is perpendicular to the surface at every point. So C is the boundary curve of the surface S. So we can generalize Green's theorem in this way, that we're relating integral around the curve to an integral over the surface that it contains in space. So that's one thing we want to get to. This is called Stokes' theorem. And then the very last thing we're going to do is concerning solids, 3-dimensional solids, and the integral of the divergence of a vector field over a solid is equal to the integral of a vector field dot product with the normal vector. So now you have some solid, and at every point you have a normal vector that's perpendicular to the solid. So this is a solid E. The boundary of a solid, boundary of E, is some closed surface S. So you can think of it as, well, an egg as opposed to its shell, or a really warped egg like this one. Okay. So we're going to generalize Green's theorem in 2 different ways. This is called the divergence, well, I'll give you a full name. It's Gauss's divergence theorem. Okay. So this is just to give you an idea of where we're going as we wrap up the chapter. So in all cases we have some integral over the interior of some region related to an integral over the boundary of that region. And we see that we have dot products here with some vector that's perpendicular to the entity that we're integrating over. Now it turns out that all of this is actually one theorem, the fundamental theorem of calculus, just applied to higher and higher dimensional regions. Because the fundamental theorem of calculus, you have f prime of x dx is f of b minus f of a when you integrate from a to b. So if you think of an interval from a to b, well, what is its boundary? The boundary is just the points x equals a and x equals b. So you can think of the normal vector at this boundary point to be just the number minus 1. You can think of the normal vector at this point just to be the number 1. So it's almost like this integral here is playing the role of these higher dimensional integrals here, and then these lower dimensional integrals correspond to this f of b minus f of a. So it's like we're taking f evaluated at the boundary dot product with a normal vector, which is just 1 or minus 1, depending on which boundary you're talking about. So all these theorems, Green's theorem, fundamental theorem of calculus, Stokes' theorem, divergence theorem, and the fundamental theorem of line integrals, they really are all just one result that's saying the same thing. There's many different contexts. And what we'll do after we finish Stewart is we're going to tie all 5 or 6, however many there are of these theorems together into one. All right. But for these, in both cases we have an integral over some surface sitting in three-dimensional space. And that's something we haven't talked about yet. So that's what today's about, just to lay the foundation. How do we define surfaces sitting in space, and how do we evaluate integrals over them? How do we compute their area? Okay. All right. And what you'll see is, a lot of what we're going to talk about with surfaces corresponds very closely to what we've been talking about when it comes to curves. So you can see the parallels between them. Talk about curves and surfaces together. So curve C is, we've been parameterizing it by vector valued function of one variable, r of t, where t is between a and b. So you can think of it as taking a line segment, just the interval from a to b, and warping it, that's what the function r does, into a curve. Could be a plane curve, could be a space curve, doesn't matter. Now, what about surfaces? Well, surface S, also parameterized, but now it's a function of two variables. You do x of u v, y of u v, z of u and v. And u and v belongs to some two-dimensional region D. A lot of times D will just be a rectangle, but not necessarily. So you're taking some two-dimensional region D in UV space, and you're warping it. That's what the function R does this time to get this sheet, this patch of surface sitting in space. Okay. So the parametric equations you just set x, y, and z equal to these component functions of your parameterization. So it's much like curves. Now they just depend on two variables because it's like you're taking a two-dimensional object and you're warping it. Okay. All right.
Alright, so the surface is warped from the square into the blob?
Essentially, yes, that you get this surface by evaluating points in this rectangle Bye bye.